We thought galaxies formed over billions of years. Slowly and methodically, this was the cornerstone of cosmology. But we were wrong. So very wrong. James Webb proved it. The first galaxies Webb looked at were there far earlier than our models allowed. It found galaxies as large as the Milky Way, when the universe was only 500 million years old. But this was impossible, because these structures should have taken billions of years to form. Some had already reached 100 billion stars. This is why physicists called them just universe breakers, because these massive structures should not have existed so early. But that's not the truly terrifying part. The real question is, if our most basic understanding of the universe's beginning is wrong, what else might we be wrong about? If that reality just shattered your brain, then like this video and subscribe to the channel, because we are about to embark on a journey that will shake everything you thought you knew about the cosmos. Here we go. For years, we thought the universe was mostly empty. That's what we saw when we looked at the night sky, a few bright stars. And between them, a vast nothingness. This was a manageable abstraction. We accepted the universe's immensity through this idea of emptiness. But the James Webb Space Telescope focused on what we thought was nothing, and suddenly, everything changed. We now know that emptiness was just an illusion. The universe is not empty. On the contrary, it is incomprehensibly full. To understand this truth, you must do a simple experiment. Hold your finger up to the night sky. Pick a spot between two stars that looks completely empty. That spot should be so small that a single grain of sand held at arm's length would completely cover it. For all previous telescopes, that was just empty space, meaningless, not worthy of attention. James Webb stared at that single spot for 12 straight hours. The image that came back contained 10,000 galaxies. Yes, you heard that correctly. Every single speck of light in that image, every spiral, every oval smudge, was an entire galaxy made of hundreds of billions of stars, each one millions of light years farther than the next. All of them contained within a patch of sky you could hide with the tip of your fingernail. This is why Webb's first deep field image, released in 2022, proved that the universe isn't empty. It is full. No matter where you look, in every direction, at every depth, there are galaxies beyond galaxies, and beyond them, more galaxies still. The emptiness we imagined was just an illusion, created by the limits of our instruments. But that wasn't the most shocking part. The real earthquake began when we realized how far away these galaxies were. Because Webb is not just a telescope, it is a time machine made of pure physics. This might sound like a metaphor. It is not. Light moves fast, but the universe is inconceivably vast. Light from the nearest star besides our Sun takes more than 4 years to reach us. Light from the center of the Milky Way travels for about 26,000 years, and light from the nearest major galaxy, Andromeda, left its source more than 2 million years ago. Therefore, any light that reaches Webb's mirror means the object that produced it has already changed, aged, or in some cases, vanished entirely. Webb is positioned 1.5 million kilometers away from us, far beyond the Moon. This allows it to reach further and further back in time, as the distance it looks at increases. The most distant objects confirmed by Webb are seen as they were more than 13 billion years ago, a time when the universe was only 3% younger than it is now. Back then, the planets in our solar system did not exist, nor did the solar system itself. The Milky Way was nothing like its present form. There were only the first generation of stars and the young galaxies gathering around them, and this is precisely where everything spun out of control. Because our standard model of cosmology predicts a clear sequence for how the structure of the universe formed. According to this model, matter in the early universe was spread out relatively evenly. Gravity slowly gathered it into clumps. These clumps formed the first small, irregular galaxies. Over hundreds of millions and then billions of years, these small galaxies merged, accreted more gas, formed more stars, and slowly evolved into the large, structured galaxies we see today. This process takes time, immense time, a galaxy the size and mass of the Milky Way should take billions of years to assemble. But Webb found galaxies that existed when the universe was between 500 and 700 million years old, a mere cosmic moment after the Big Bang, which had already reached enormous masses. One candidate, when observed in the Webb data, appeared to contain nearly as many stars as the modern Milky Way. According to the Standard Model's timeline, that galaxy should not have been anywhere near that size yet. This situation created an anomaly that astronomers dubbed universe breakers. Because these findings aren't just about mass, some of these early massive galaxies appear to contain populations of stars that formed even earlier and had already aged. This pushes their formation timeline even further back, into a window that the Standard Model considers impossible. Of course, scientists are cautious about these findings, because confirming the exact distance and mass of a very faint, very distant galaxy takes time. Some initial candidates have had their estimates revised after closer scrutiny. But, as of 2024, several of these massive early galaxies have had their distances and approximate masses spectroscopically confirmed, and they remain a tension that current models genuinely struggle to explain. These galaxies are real, their sizes have been measured, and the question of how they managed to grow so big, so fast, is one of the most active areas of research in cosmology right now. Whatever the answer, it will change the entire timeline of how our universe assembled itself, because what Webb found inside these ancient galaxies is where the real pressure begins. Hidden in that ancient light is a problem our leading theory of cosmic history cannot yet explain, and that problem makes us question even our most basic idea of how it all began. Because what Webb found at the center of these ancient galaxies, was something at least as impossible as the galaxies themselves. Monsters, supermassive black holes, with masses of billions of suns. As these black holes devoured the gas and dust around them, they released so much energy that each one shone brighter than all the stars in its entire host galaxy combined. We call these objects quasars, and the quasars Webb found were already there, before the universe had even turned 1 billion years old. This seems to violate one of the most fundamental rules of physics, because a black hole can only feed at a certain rate. This is called the Eddington limit. You can think of this limit like trying to drink water from a fire hose. At a certain point, the pressure of the water pushes you back, and you can't drink anymore. It's the same for black holes. The radiation coming from the matter they swallow prevents more matter from falling in. Therefore, the time it should take for a black hole, starting from a stellar remnant, to reach a mass of billions of suns, is longer than the age of the universe at that time. But the black holes Webb found were there. Defying all calculations, they seem to have grown faster than time itself. This situation fundamentally shakes all our ideas about how the first black holes formed. Perhaps the initial seeds were not from stars, but from the direct collapse of massive gas clouds. Perhaps galaxy mergers in the early universe caused black holes to merge as well, growing at a monstrous rate. One thing is certain: the existence of these black holes is not just a mystery in itself, but it could also be a key to why their host galaxies grew so fast. This alone could have rewritten all the books. But this was not the only anomaly Webb found, because it's not just the objects within the universe, but the behavior of the universe itself that carries a massive question mark. We've known since Edwin Hubble's observations in the 1920s that the universe is expanding. Measuring the rate of this expansion has been one of the most fundamental goals of cosmology for decades, and we have two main methods to make this measurement. The first method is to look back in time to about 380,000 years after the Big Bang. We study the cosmic microwave background radiation, and from this data, we calculate what the universe's expansion rate should be today. The number found using this method is about 67 kilometers per second per megaparsec. The second method looks at the nearby universe at the present day. We directly measure how fast galaxies are moving away from us, using standard candles like supernovae. The number found with this method is about 73 kilometers per second per megaparsec. 67 versus 73, these two numbers do not agree. We call this ongoing tension the Hubble tension. Many scientists hoped that this might be a measurement error that would disappear with more precise data. This is where Webb came in. Webb's sharp vision was used to eliminate potential errors in the local measurements. The result, Webb confirmed, that the local measurement is largely correct, meaning the 73 number is valid. This, instead of eliminating the tension, made it even sharper. This is not a rounding error. This is a crack in the foundation of cosmology. Either something is missing in our model of the early universe, or there's an error in how we understand the local universe, or in the most disturbing possibility, the law of cosmic expansion itself might be changing over time. Both the past and the present of the universe are in contradiction with each other, and as if that weren't enough, the universe itself has turned out to be a far different place than we expected. Webb's first deep field image showed not only things we'd never seen before, but also how much there was. A 2016 study using Hubble data had already increased the estimated number of galaxies in the observable universe from 200 billion to 2 trillion. Webb's observations are now solidifying this insane number even further, because Webb can see galaxies that are so faint, so small, and so distant that previous telescopes could never see them. These are the building blocks that merged over billions of years to form large galaxies like the Milky Way, and the early universe is filled to the brim with these small structures. Now let's take this statistic to the next level. If we accept that every star, on average, hosts at least one planet which current data supports, then we can do a simple calculation. 2 trillion galaxies, each with hundreds of billions of stars. This means quintillions of planets. In writing, a 1 followed by 18 zeros. This is a number that has no meaningful equivalent in human experience. This makes the question, are there other planets, meaningless. That's no longer the question. The question is now, of this unimaginable number of worlds, which ones might possess the right chemistry for life? This is the new reality Webb has presented to us. Black holes that grew too early, an expansion rate that doesn't agree with itself, and a universe so crowded it's beyond imagination. These findings have torn up the old map of cosmology and replaced it with a vast new continent filled with unknowns. We are now questioning not just what we know, but what we thought we knew. These are the outlines of the picture, the theoretical frameworks. But what is the actual evidence that fills this frame? What concrete discoveries reveal these massive galaxies, these strange black holes, these conflicting measurements? It's time to put the concepts aside, because in the next section, we will look directly through Webb's eyes and see the evidence. And now comes the real shock. Because, theories and concepts aside, the actual findings are far more disturbing. They were there to test the theory, but they ended up breaking it. These are the impossible objects Webb found that silenced the world of cosmology. The first blow came in 2023. A team of astronomers published a paper identifying 6 galaxies in Webb's early data, and they called them, in their own words, universe breakers. The phrase caught attention, but the science behind it was an even bigger shock. These galaxies existed when the universe was between 500 and 700 million years old. This is a mere cosmic blink after the Big Bang, but their masses were unbelievable. One of them appeared to have as many stars as the Milky Way contains today. This should not have happened. It absolutely should not have happened, because, according to our standard model, a galaxy needs billions of years to accumulate that many stars. It needs to slowly gather gas, merge with smaller galaxies. But this galaxy had appeared almost overnight in the universe's timeline. It was like a baby growing to the size of a full-grown adult in a single day. The laws of physics didn't seem to allow it. Astronomers checked the data again and again. Maybe it was a measurement error. Maybe these galaxies were actually closer, and their light was deceiving us. But spectroscopic analysis, the process of reading the chemical fingerprint of light, confirmed the distance. These galaxies were truly that far away, truly that early, and truly that big. This is why the scientific community was split in two. Either star formation in the early universe was far more efficient than we thought, or our most fundamental model of how galaxies form was fundamentally wrong. But this was only the beginning. Because the problem wasn't just the galaxies themselves, the things inside them were even stranger. When Webb looked inside some of these early massive galaxies, it encountered another impossibility. Some of these galaxies had already fallen silent, meaning they had stopped forming stars. This is like a city being built in just a few years, and then being completely abandoned. According to the standard model, a galaxy going quiet is a long process. It needs to exhaust its gas reserves, or have its gas blown out by the energy from its central black hole. This too takes billions of years. But these galaxies Webb found had both produced all their stars and retired before the first billion years of the universe were even over. This implied that the supermassive black holes at their centers must have been incredibly active and powerful. These black holes must have heated and ejected the surrounding gas so violently that they completely halted new star formation. This is a possibility. But this possibility brings with it another impossibility. How did those black holes themselves grow so fast? So in trying to solve one mystery, we found ourselves in the middle of an even bigger one. These silent galaxies were concrete evidence that the early universe was not a calm and slow place, but on the contrary, it underwent an incredibly violent and rapid evolution. And then came the quasars, the brightest, the most powerful, the most distant light sources. Webb studied a quasar called UHZ1. This quasar was shining when the universe was only 470 million years old. That's within the first 3% slice of time after the Big Bang, but the black hole inside it had a mass between 10 and 100 million times that of the Sun. Stop and think, 470 million years. That amount of time is not enough for a black hole, feeding at the Eddington limit, the physically possible maximum speed, to reach this mass. The math didn't add up. There wasn't enough time. This black hole existed before the time required for it to exist. This discovery strengthened the direct collapse theory, the idea that the first black holes formed not from stars, but from giant gas clouds. Because only if you start with a seed of tens of thousands of solar masses can you create this monster in such a short time. But even this is not a sufficient explanation on its own. Perhaps black holes were fed by super Eddington accretions that exceed the theoretical limit. Perhaps some physics we don't know about was at play. What is certain is that UHZ1 and similar quasars proved that the gravitational engines that reshape galaxies, change chemistry, and extend tens of billions of light years away were already running, even in the first moments of the universe. All these discoveries were about the universe itself. But Webb also had one eye turned closer to our own galaxy, and what it found there was perhaps the most personal shock of all. Webb studied the atmosphere of an exoplanet, a gas giant named WASP 39b 700 light-years away from us. And there, for the first time ever, it detected carbon dioxide in an exoplanet's atmosphere. This, by itself, was a major achievement. But the real bombshell dropped when it found sulfur dioxide. Because sulfur dioxide is formed by photochemistry, when light from the planet's star interacts with other molecules in the atmosphere. Do you know what this means? Webb didn't just read what was in another world's air, it read the chemical reactions actively happening in that world's sky. It's weather. This meant we could now study exoplanets not just as existing objects, but as living dynamic systems. These massive galaxies, impossible black holes, and dynamic planetary atmospheres, when they all come together, the picture that emerges turns everything we know upside down. But how do we explain all these findings? What is the mechanism behind these universe-breaker galaxies? What powered these fast-growing black holes? The answers to these questions lead us to an even deeper mystery, the invisible skeleton of the universe, because the thing that holds all this structure together, and perhaps the real reason behind all these anomalies was dark matter itself. This is why Webb focused on the largest structures in the universe, galaxy clusters, massive systems that hold hundreds or even thousands of galaxies together with gravity. The visible mass of these clusters is not enough to hold them together. What holds them together is an invisible skeleton, dark matter. Webb uses a technique called gravitational lensing to map this skeleton, and what it's finding is bleeding another wound in the standard model, because Webb has observed protoclusters, the ancestors of modern galaxy clusters, when the universe was between 1 and 3 billion years old, and some of these early structures were far more massive and far denser than the standard cold dark matter simulations predicted for that era. One case showed multiple massive galaxies clustering together so tightly in the early universe that they formed a gravitationally bound structure. If this is confirmed, it would mean a cluster that assembled far earlier and far more rapidly than the model expected. These anomalies are not isolated. Webb is finding these types of early massive structures at a frequency that suggests they are forming with an efficiency and speed that the model cannot capture. This means the universe is building its largest structures in less time than the instruction manual allows. But massive structures weren't the only anomaly Webb uncovered. Sometimes, the biggest secrets are hidden in the smallest things, or even in things that shouldn't exist at all. Population 3 stars. They are the first stars in the universe, entirely theoretical. No one had ever seen one. Because they should have been made of only the 3 elements that existed after the Big Bang: hydrogen, helium, and trace amounts of lithium. They should have contained none of the heavier elements like carbon, oxygen, and iron that make up planets and life. Therefore, theoretical models predicted these stars to be incredibly massive, tens to hundreds of times the mass of the Sun, extraordinarily bright, and very short-lived. They should have burned fast, died in powerful explosions, and scattered the first heavy elements into the cosmos. Webb cannot directly image such a star. But in 2023, it detected a particularly strong signal in the spectrum of a galaxy that existed about 400 million years after the Big Bang. The signal came from ionized helium, and the unusual strength of this signal was consistent with the presence of extremely hot, very massive stars, like population 3 stars. This is not proof, not yet. But we may have heard, for the first time, the whisper of the universe's first light. If this whisper is confirmed, it means we have found the keystone between a universe made of only light elements and a universe capable of creating planets and life. The origin of everything in your body heavier than lithium traces back to those invisible first stars. Webb's discoveries were not limited to the distant past. Sometimes the most surprising things can be right under our noses. Webb imaged the pillars of creation. The massive cloud of gas and dust 6,500 light-years away Rossestwal, made famous by Hubble's iconic 1995 photograph. Hubble's image was magnificent. But Webb's infrared eyes pierced through the dust, and there, for the first time, hundreds of newly forming stars embedded deep within the pillars were revealed. These once opaque massive structures were transformed into stellar nurseries, and the most incredible part was this: the pillars themselves were being destroyed by the radiation from these new, hot stars being born within them. Creation and destruction in a single frame at the same time. This image is far more than an aesthetic triumph, because it concretely shows that star formation is an ongoing process in our galaxy and others. The Milky Way produces a few solar masses of new stars on average each year, and the chemical composition of the gas and dust from which these stars are born can now be analysed with greater clarity than ever before, thanks to Webb. This brings us back to the most fundamental question about the origin of life. These massive galaxies, impossible black holes, conflicting measurements, an invisible skeleton, and self-destructing stellar nurseries. Every piece Webb finds is more astonishing than the last, each one a revolution in its own right. But when they all come together, they show that the universe is not only bigger than we knew, but also weirder, more violent, and much, much faster. So how does Webb make all these incredible observations? What technological marvels are required to capture a single photon from 13 billion years ago? How does that mechanical flower that delivers the light of these massive galaxies and impossible black holes to us actually work? Now, it's time to take a closer look at the incredible engineering behind these shocking discoveries. the time machine itself, because to understand what Webb has found, we must first understand how it sees. And this telescope itself is at least as extraordinary as the universe it discovers. And this telescope itself is at least as extraordinary as the universe it discovers. But how does it make all these incredible observations? How is it possible to capture a single photon from 13 billion years ago? Let's slow down the pace a bit. Let's move from the shocking headlines to the depths of the incredible engineering and physics that make those headlines possible. Because, to fully understand what Webb has found, we must first understand how it sees. And this is made possible by the convergence of multiple technological revolutions. The first and most fundamental mechanism is the answer to why Webb is a time machine. This is a pure rule of physics, born from the combination of the speed of light and the expansion of the universe. Think of it this way: when we say Webb has captured a photon from a galaxy 13 billion light-years away, it means that photon has traveled for 13 billion years to reach the telescope. But this journey did not happen in a static space. While the photon was on its way, space itself was expanding like a balloon. Therefore, when the photon began its journey, its source galaxy was much closer to us. But when the photon's 13 billion-year journey ended, and it reached Webb's mirror, that galaxy had now been dragged to a position estimated to be more than 40 billion light-years away from us. The light travelled for 13 billion years, but its source is now 40 billion light-years away. This seemingly contradictory situation is resolved when you understand that in an expanding universe, distance changes depending on when you measure it. This is why Webb sees not just the distant key, but also the past. And the reason it can see this past is a phenomenon called redshift. Just as the siren of an approaching ambulance gets higher in pitch and then lower as it moves away, the wavelength of light from galaxies moving away from us also stretches. This stretching causes the light to shift towards the red end of the spectrum. The farther a galaxy is, the faster it moves away, and the more its light is redshifted. Webb is designed to measure this redshift with incredible precision. This is why it can distinguish the difference between a galaxy formed 300 million years after the Big Bang and one formed 500 million years after. This 200 million year difference over a 13 billion year time span is within Webb's measurement capability. But to capture this ancient and redshifted light, Webb itself had to be extraordinary. The second key mechanism is Webb's infrared vision and the incredible coldness that makes it possible. The previous great telescope, Hubble, operated mainly in visible light. But most of the earliest and most distant galaxies are hidden behind dense clouds of gas and dust. Their light has been stretched and dimmed during its journey of billions of years. For Hubble, seeing these galaxies was like trying to read a sign behind a thick fog. It could only see a faint trace. Webb, on the other hand, operates at infrared wavelengths. Infrared radiation is essentially heat, and this heat radiation passes through dust clouds, much like a radio signal passes through a wall. What was fog for Hubble is transparent for Webb. This single difference means Webb can see not just farther, but deeper in time. But there's a problem. If Webb itself were warm, its own heat would blind its detectors. Just like your eyes are dazzled after looking at a bright object on a sunny day. Therefore, Webb had to be one of the coldest places in the known universe. The telescope operates at about -233 degrees Celsius. This temperature is colder than the surface of Pluto. This is just a few degrees above absolute zero, the theoretical minimum temperature where all thermal motion ceases. To achieve this incredible coldness, Webb has a giant, 5-layered sun shield, the size of a tennis court. Each layer is thinner than a human hair. This shield blocks the heat from the sun, the Earth, and the Moon. On the cold, shaded side of the shield, the temperature drops to these incredible levels. This is the fundamental engineering marvel that allows Webb to hear the faintest, oldest heat signals of the universe, without interference from its own heat. The third mechanism is how Webb collects and focuses this faint light, its massive and unique mirror. Webb's primary mirror is 6.5 meters in diameter. This is much larger than Hubble's 2.4 meter mirror, and in a telescope, mirror size is everything. A larger mirror means collecting more light. This means being able to see fainter and more distant objects. But this mirror is not a single piece, because there was no rocket large enough to send a 6.5-meter single-piece mirror into space. So engineers designed the mirror as a foldable structure, made of 18 hexagonal segments, just like an origami flower. These segments are made of beryllium, an ultralight and durable material, and are coated with a thin layer of gold. Gold is exceptionally efficient at reflecting infrared light. Each of these 18 segments was polished with nanometer-precision, a billionth of a meter, because any surface imperfection at this scale would turn even the faintest signals into a blur. After the telescope reached its orbit in space, each of these 18 segments had to be aligned to form a single, perfect, smooth surface. This process took weeks and involved adjustments requiring a precision of less than 1,000th of a millimeter. This mechanical flower was designed to capture those faint photons that have almost no energy left after a 13 billion year journey. And when these photons reach Webb's sensitive detectors, they carry the fingerprint of the galaxy they came from. All these fundamental mechanisms that make Webb so powerful. Its knowledge of redshift that allows it to look back in time, its cold infrared vision that allows it to see through dust, and its giant, segmented mirror that collects that faint light. They all work together, like a symphony. But it's not just about collecting light. The real magic of Webb lies in how it analyzes the information from that light. Because Webb doesn't just take pretty pictures, it separates light into its components and reads it like a chemical barcode. This is a technique called spectroscopy, and the way Webb uses this technique allows it to measure everything from the atmospheres of exoplanets to the expansion rate of the universe. Because the information a photon carries is the story not just of where it came from, but also of what it's made of. And Webb's ability to read this story leads us to another technological revolution. Not just seeing the universe, but practically smelling it. Because what Webb does is exactly that. Analyzing the chemistry of distant worlds and galaxies, despite the billions of light years in between. And the mechanism behind these analyses is one of Webb's most powerful weapons, spectroscopy. This is why Webb doesn't just see the universe, it practically smells it. Spectroscopy is the process of splitting light into its component colors, a rainbow. But this is much more than a simple prism. Because when light from a star or galaxy is separated into this spectrum, dark or bright lines appear on it. These lines are the fingerprints of the atoms and molecules that the light encountered on its journey, or that were present at its source. Every element, every molecule, absorbs or emits specific wavelengths of light. Just like every person has a unique fingerprint, Webb has special instruments designed to read these fingerprints. This allows it to measure a galaxy's chemical composition, temperature, mass, and age, despite the billions of light years in between. For example, transit spectroscopy, the mechanism for analyzing an exoplanet's atmosphere, is exactly this. As the planet passes in front of its star, some of the starlight filters through the planet's atmosphere. Molecules in the atmosphere absorb specific wavelengths corresponding to their own fingerprints. Webb detects this missing light, the dark lines in the spectrum. When it finds carbon dioxide, it sees that specific infrared wavelengths are missing. When it finds water vapor, it sees that other wavelengths are missing. This method is so sensitive that Webb can determine not only which molecules are present, but also how abundant they are. Hubble could use this technique, but Webb's infrared sensitivity and larger mirror allow it to detect a much wider range of molecules and much fainter signals. This means the capacity to trace molecules that were previously completely inaccessible, especially those we associate with life. But there is another seeing technique that Webb uses, and this one uses a trick of nature itself. The fifth mechanism is gravitational lensing. Albert Einstein's general theory of relativity predicts that mass bends spacetime, and light travels along this bent spacetime. You can think of this effect like this. Place a heavy bowling ball on a rubber sheet. The sheet sags. Now roll a marble across the sheet. the marble will curve towards the dent created by the bowling ball. Light does exactly this. As light from a very distant object passes by a massive object on its path, like a giant galaxy cluster, it bends towards the gravity well created by that mass. This bending causes the galaxy cluster to act like a giant natural telescope. It magnifies, distorts, and sometimes even creates multiple images of the much more distant objects behind it. This is one of Webb's greatest advantages, because, thanks to this natural magnifier, it can see galaxies that are too faint and too distant to be seen even with its own power. A background galaxy can become 10, 20, or sometimes more than 50 times brighter thanks to these natural lenses. Webb specifically targets known strong lensing clusters like El Gordo, the fat one, or Pandora's cluster, to look into the deepest and oldest corners of the universe. This method is much more effective than Hubble's because Webb's natural resolution and sensitivity allow it to resolve the fine details of these lensed images. The shapes of the distorted arcs and lines contain invaluable information about the mass distribution of the cluster forming the lens, especially about where the invisible dark matter is concentrated. This is why, in every lensing observation, Webb studies both the foreground lens, the near universe, and the object behind it, the distant universe, at the same time. It kills two birds with one stone. And finally, there is an invisible architecture that holds all these mechanisms together and allows Webb to function as a whole, its position and stability. Webb is not in orbit around the Earth, because the Earth itself is a major heat source. So is the Moon. That's why Webb is located 1.5 million kilometers away from Earth, at a special point in the direction away from the Sun, the second Lagrange point, known simply as L2. This point is a point of equilibrium. Here, the gravitational forces of the Sun and Earth balance Webb's orbital motion, allowing it to always remain with its back to the Sun, Earth, and Moon, just like a dancer, spinning in perfect balance with their partner. This ensures that Webb's massive sunshield is always facing the heat sources, and its sensitive optics remain constantly in the freezing cold of deep space. To stay in this orbit, Webb needs to perform periodic small orbit correction maneuvers. But this point is so stable that the amount of fuel required for these maneuvers is minimal. In fact, Webb's launch was so precise and perfect that it used less fuel than planned to settle into its orbit. This means the telescope's scientific operational life could be extended from the initially planned 10 years to potentially 20 years or more. Hubble was in an orbit that could be repaired and maintained by astronauts. But Webb is too far away for a human mission to reach. After launch, every single one of the more than 300 single points of failure had to work flawlessly, and so it did. This incredible engineering achievement is the fundamental pillar that allows the telescope to conduct science every day, every hour without interruption. The spectroscopes that read redshift, the cold infrared detectors that see through dust, the gold-plated mirror that collects faint light, the gravitational lensing that creates natural magnifiers by bending the universe, and the L2 orbit that holds it all in perfect balance. This is Webb's secret, the symphony of these mechanisms, each an engineering marvel in its own right, working in unison. But all this incredible technology, all this physics and engineering is just a tool. The real purpose is to use these tools to seek answers to the universe's biggest questions. And now that we understand how this tool works, it's time to get back to the exciting part. What do we find when we turn this perfect machine on the universe's most disturbing gawas, most unsolved, most shocking mysteries? The Hubble Tension, the nature of dark energy, and that final frontier at the very edge of existence. Because what we've seen so far was only the beginning. The real climax starts now, and what Webb finds could reshape not just the past of the universe, but its future as well. Because the two biggest mysteries, how the universe began and how it will end, are still waiting to be solved, and Webb, the two biggest mysteries, how the universe began and how it will end, are still waiting to be solved, and Webb is looking right into the heart of those mysteries. And now comes the real miracle. Everything we've talked about so far was just a preparation for this moment. We've understood the technical details. We've drawn the conceptual framework. But now, we've reached those moments that push the limits of that frame and technique, that tremble the boundaries of reason and physics, that rewrite the history of cosmology. We are increasing the speed to maximum, because these are Webb's greatest moments. These are the findings that took scientists' breath away, made headlines, and made textbooks obsolete. These are the moments when the deepest secrets of the universe were revealed. Get ready. Because the climax starts now. The first earthquake, the Hubble Tension, 67 versus 73, a stalemate that has lasted for years, cosmology's biggest crisis. Many hoped it was a blur error, caused by the Hubble telescope's inability to distinguish stars in crowded galaxy regions. Maybe they were measuring multiple stars as a single one. Webb was designed to destroy this hope, and it did. The team led by Nobel laureate Adam Rees turned Webb to the heart of this problem. The result? Published in 2023, and it shook the scientific world. Webb's unparalleled sharpness resolved the Cepheid variables, the universe's distance markers, one by one with a clarity never seen before. The margin of error dropped to almost zero, and the number? It didn't change. The expansion rate of the local universe remained nailed at 73 kilometers per second per megaparsec. This proved that the problem was not a measurement error. This was a crisis. But now, it was a more precise, more certain, more undeniable crisis. Because Webb didn't just confirm a number, it sealed the physical chasm between the early and late universe. We now know that either our way of interpreting the light left over from the Big Bang is wrong, or the universe itself has a hidden component, like an early dark energy, that changed its identity between its youth and old age. Webb didn't solve a problem, it threw the depth and reality of the problem in our faces. But Webb's real specialty was the past, the deepest past, and what it found there overshadowed even the Hubble tension. Introducing JADES-GS-Z13-O. That's not a name, it's a coordinate. The address of the most distant, most ancient galaxy ever seen in human history. Its light travelled for more than 13.4 billion years to reach us. This means it's the universe as it was just 325 million years after the Big Bang. 325 million years, a long time for Earth history. But for cosmology, it's a moment, a blink of an eye, and in that blink, JADES-GS-Z13-O was there. It wasn't just existing, it was a galaxy, filled with stars, structured. This was impossible, physically impossible, because our model said that at that time, only single stars or at most small star clusters could have formed. There wasn't enough time for a galaxy, a massive structure of hundreds of millions of stars held together by gravity, to form. The required evolutionary process of hundreds of millions of years just didn't fit into a 325 million year old universe. But it was there. Webb saw it, took its spectrum, confirmed its distance. It was like seeing the roof of a building being built before its foundation. Scientists were in shock. Papers were filled with phrases like severe pressure on the structure formation timeline. This was the polite way in scientific language to say, we don't know how this happened. JADES-GS-Z13-O by itself brought an entire theory of how galaxies form brought into question. And it wasn't the only record breaker Webb found. It was just the tip of the iceberg. We went deeper, and there we found the monsters that not even light itself can escape. But those monsters shouldn't have been there either. CEERS-1019, a galaxy, existed when the universe was 570 million years old, but the black hole at its center had a mass of 9 million times that of the Sun. This was much larger than the mass of Sagittarius A. The black hole at the center of the Milky Way at that time, and even this record was quickly broken. Webb found the monster in the UHZ-1 quasar, existing when the universe was 470 million years old, between 10 and 100 million solar masses. The growth rate of these black holes comically exceeded physics' Eddington limit, the limit of how fast a black hole can eat without exploding. This was like a human eating an elephant in a single sitting. It was not possible. But Webb's data was there. The spectroscopic evidence was definitive. This situation pushed scientists towards heavy seed scenarios. The idea that the first black holes came not from light seeds, born from the death of a single star, but from heavy seeds, formed from the direct collapse of giant gas clouds of tens of thousands of solar masses. This helps solve the equation. But it also raises a new question. Why did those giant gas clouds collapse directly into a black hole instead of turning into stars? These black holes are not just anomalies, they are the most concrete evidence that the early universe was a much more violent, much faster, and much more efficient place than we thought. They were the engines of the universe, and it seems those engines had started running long before we thought we had turned the ignition. And then came the most incredible, the most mind-boggling, the most poetic discovery: gravitational lensing using the universe's own telescope. Webb looked at a giant galaxy cluster called SMACS 0723. This cluster was so massive that it bent space-time, acting as a giant magnifying glass for the objects behind it. And behind that magnifying glass, Webb discovered the most distant individual star in history, Earendel. It means morning star. This was not a galaxy, not a quasar, a single star. Its light had travelled 12.9 billion years to reach us. The universe was only 900 million years old. Under normal circumstances, seeing a single star from this distance is impossible. When even the collective light of millions of galaxies looks like a faint smudge, a single star, unimaginable. But gravitational lensing had amplified Earendel's light by thousands of times. Webb was looking at the right place at the right time, and it caught that incredible moment of alignment. This is not just a record, this is a miracle. This is a gift that gives us the opportunity to directly study the chemical composition, mass, and properties of the first stars of the universe. Earendel was likely at least 50 times more massive than the Sun, and millions of times brighter. It was one of the first lights shining in that dark age of the universe, and Webb, 13 billion years later, caught its faint light. This isn't finding a needle in a haystack. This is looking for a needle in a haystack in another galaxy, and Webb just found that needle. The evidence that sealed the Hubble Tension, galaxies that shouldn't have existed at the beginning of time, massive black holes that defy physics, and the whisper of a single star from 13 billion years away. These are just a few glimpses of the new universe Webb has presented to us, each one a paradigm shift in its own right, all of them together a revolution. But what does all this mean? What do these impossible findings tell us about the nature of the universe? What does the picture that emerges when we put these pieces together look like? Because each of these discoveries doesn't just offer an answer, it also raises dozens of new questions, and these questions lead us to the most fundamental philosophical consequences of our existence. Because what Webb is showing us is not just a science lesson, it is also a mirror. And what we see in that mirror is our own smallness, and the universe's incomprehensible creativity. Therefore, the meaning of these findings is much more than just a cosmological correction. It is a revolution that makes us question our most fundamental assumptions about our place in the universe. The picture that emerges when we put these pieces together is not a calm, orderly, and predictable universe. On the contrary, it is a violent, chaotic, efficient universe that pushes the limits of our imagination, and the greatest shows of this universe are just beginning. The tempo is not slowing down, because there are more anomalies that Webb has found, each one more shocking than the last. The void, the cosmic void, one of the largest and most mysterious structures in the universe. We knew these voids existed, but their size and effects were a complete enigma. Introducing the Bhuta's Void, also known as the Great Nothing. When discovered, its scale was unacceptable, a sphere of nothingness, 330 million light-years in diameter. Inside, there are almost no galaxies. You could travel for millions of light-years within it and not encounter a single major galaxy. Standard models predicted that matter clusters together through gravity to form filamentary structures, leaving voids between them. But a void this large? This was much larger than the models predicted. Webb cannot directly image the inside of these voids, because there is nothing to image there. But what Webb does is measure the distances and motions of the galaxies on the edges of these voids and the filamentary structures around them with incredible precision. And these measurements allow us to map the cosmic web, the largest scale architecture of the universe. These maps, updated with Webb's data, show that the filaments are denser, the nodes are more crowded, and the voids are emptier. The texture of the universe is sharper, more contrasted than our models predicted. This shows that gravity is bringing matter together more tightly, working more efficiently than we thought. And the question of what lies behind this efficiency brings us back to the same place: the universe's invisible skeleton, dark matter. Perhaps the nature of dark matter is more complex than we thought. Perhaps it interacts not just through gravity, but in other ways we don't know about. Massive structures like the Bhuta's void are not just anomalies. They are the quietest, but most powerful evidence that there is something we don't understand in the fundamental architecture of the universe. But the architecture of the universe is not just made of voids. There is also an invisible force that holds that architecture together, that governs everything: dark matter itself. Webb uses gravitational lensing to map dark matter, and these maps have revealed a new anomaly that shakes the theory: the bullet cluster. About 3.7 billion light-years away, the result of a head-on collision of two giant galaxy clusters. This is one of the most energetic events to occur in the universe since the Big Bang. During the collision, the hot gas in the clusters, the normal matter we know, slowed down due to electromagnetic forces and accumulated in the center of the collision zone. But dark matter, since it only interacts through gravity, it passed through each other like a ghost and was thrown ahead of the gas. Data from the Chandra X-ray Observatory showed where the gas was, and Webb and Hubble's gravitational lensing maps showed where the total mass, the dark matter, was, and the two were not in the same place. This was the first ever direct visual evidence of the separation of dark matter and normal matter. This was the irrefutable proof that dark matter is not just a theoretical convenience, but a real thing that exists and behaves differently from normal matter. This image was called the tombstone of all alternative gravity theories that deny dark matter, because this separation was something that none of those theories could explain. The bullet cluster, with Webb's contributions, has given us the clearest clue yet about the nature of this mysterious substance that makes up about 27% of the universe. But we still don't know what it is. It remains physics' greatest mystery. And then we change the scale again, from the largest to the smallest, from the most crowded to the rarest. While studying the dust around a star system, Webb found something completely unexpected: complex organic molecules, not just simple molecules like methane or carbon dioxide, carbonyl sulfide, methyl cyanide, and various carbon chain molecules containing carbon-nitrogen bonds, which are fundamental to the chemistry of amino acids, the building blocks of proteins. These molecules were found inside an interstellar cloud. What does this mean? When a star and planetary system form, they inherit the chemical inventory of the cloud they form within. If complex organic molecules are common in interstellar space, this means that the chemical precursors for life are delivered to the surfaces of countless planets throughout the galaxy as a routine part of planet formation. This does not prove that life is common, but it shows that the raw materials necessary for life are sprinkled in every corner of the universe. This incredibly strengthens the idea that life may not be a coincidence, but an inevitable outcome of chemistry. By making this detection, Webb has created a revolution in the field of astrobiology. We are no longer just asking, is there life? We are now asking, where and how does the chemical journey required for life to begin start? And it seems that journey begins not on a single planet, but in that cold, dark space between the stars. And finally, the most personal, most existential discovery: the TRAPPIST-1 system, just 40 light-years away from us, 7 Earth-sized planets orbiting an ultra-cool dwarf star. With multiple planets in the habitable zone, an orbit where liquid water could exist on their surfaces. It is the most promising place for our search for life outside the solar system. Webb looked at one of these planets, TRAPPIST-1c, and it measured the planet's thermal emission. The result? The planet's surface appeared to be bare rock, with no thick atmosphere. This may sound like a disappointment at first, but it's not. This is a revolution, because this was the proof that for the first time in human history, we have the ability to characterize the atmosphere of an Earth-sized exoplanet. We could even tell if there was an atmosphere or not. This was something that was previously science fiction. Now, it is an observational fact. TRAPPIST-1c may not have an atmosphere, but observations for the other planets in the system are ongoing. One day, Webb may find a biosignature in the spectrum of one of those planets, where oxygen, methane, and carbon dioxide are all present at the same time. This would be a combination that is very difficult to explain without biological processes. That day could be the most important day in human history. That day could be the day we learn we are not alone in the universe. Webb opened that door for us, and finding out what's behind that door is now just a matter of time. All these discoveries, the massive voids that change the texture of the universe, the concrete proof of dark matter, the chemical origins of life, and the ability to read the air of another world. This is the climax Webb has presented to us, a series of dizzying, paradigm-shattering and reality-redefining moments. But now it is time to stop and think. After this frantic pace, let's take a breath. Because all these numbers, all these records, all these scientific revolutions bring with them a single philosophical question. What does this mean for us? In this massive, violent, chaotic, and yet incredibly creative universe, on a small, blue planet, in a quiet arm of the Milky Way, where do we stand in all this cosmic drama? We are no longer just looking at the universe. The universe, through Webb, is looking back at us, and the story it's telling us is very different from what we expected. Because the next chapter of this story goes beyond physics and chemistry and the next chapter of this story goes beyond physics and chemistry and touches our hearts directly. And now, after all this dizzying speed, it's time to stop and take a breath. Time to stop and think. Because this new universe that Webb has shown us is not just about numbers and records. It forces us to ask us more sharply than ever before the question of who we are and what our place is on this cosmic stage. In this massive, violent, chaotic, and yet incredibly creative universe, on a small, blue planet, in a quiet arm of the Milky Way, where do we stand in all this cosmic drama? This new reality that Webb presents to us is filled with a series of deep, unsettling, but also beautiful paradoxes. Let's face those paradoxes now. The first paradox is about scale. On one hand, there is the unimaginable vastness that Webb shows us, the 93 billion light-year expanse of the observable universe, the 2 trillion galaxies within it, the hundreds of billions of stars in each one, and the quintillions of planets orbiting those stars. This is a scale that the human mind refuses to grasp. But, on the other hand, there is the incredible smallness of the being observing this universe. You, me, us. We are a species just over 1.5 meters tall, with an average lifespan of 80 years, that hasn't even managed to leave its own solar system. How can these two truths coexist? Was this immense stage of the universe set for such a tiny audience? Here is the tragic truth. We will never go to those magnificent galaxies Webb shows us, those glowing nebulae, those mysterious planets. The light from JADES-GS-Z13-O from 13.4 billion years ago is reaching us, but the distance to that galaxy's present form is too great to be crossed even at the speed of light. This is a beauty we cannot touch, a knowledge we cannot reach. It is the deep, melancholic sorrow of standing in front of a cosmic storefront, knowing we can never go inside. But, and here is that magic word, but. The fact that we can never go there does not mean we cannot learn their story. Webb is our extension, our eye, our ear. It allows our minds to travel to those distant worlds, transcending our physical limitations. We cannot set foot on the soil of those galaxies, true, but we can learn their chemical composition, their formation history, the stories of the stars within them. This is perhaps an even greater miracle. Our ability to form such a deep mental connection with a universe to which we are not physically bound. You're at the very center of this paradox. You are smaller than a grain of sand in this vast universe. But you're also one of those rare beings who can comprehend that universe, give it meaning, and stand in awe of its beauty. The atoms that make up your body were forged in those distant stars billions of years ago. And now, with the brain made of those atoms, you're looking back at the stars where your ancestors were born. What is this, if not the universe watching itself? The second paradox is about time. On one hand, there is a 13.8 billion-year-old universe, a past close to eternity, and a future that will last for billions more years, perhaps an eternity. But, on the other hand, there is the incredible brevity of our existence. All of human history takes up less than a second on the cosmic calendar. Your life is just a vibration of a moment within that second. What meaning can such a transient existence have in such an ancient universe? The tragic truth is, we are witnessing only a tiny moment of the universe's grand story. The universe existed before us. It will exist after us. The galaxy mergers, the birth and death of stars that occurred over billions of years, we see them only as a snapshot in time. When Webb captures the image of a galaxy from 13 billion years ago, we know we will never see that galaxy as it is today, because the light carrying that information will only reach us in another 13 billion years. We are an audience watching not the movie of the universe, but only its frozen frames. This is the melancholic awareness of the billions of years of story we missed, and the billions of years of future we will never see. But again. The fact that we exist for only a moment does not mean that moment is worthless. On the contrary, it makes that moment priceless. We are part of that special moment when the universe can observe itself. For billions of years, the universe existed, dark and unconscious. It just was. But then, on this small planet, we, made of stardust, emerged and said to the universe, "How vast you are." At that moment, everything changed for the universe too, because for the first time, it had a witness. For the first time, it had a meaning. Perhaps the purpose of the universe's existence was to create this moment, the moment when someone would look at it and be amazed. You are in that moment. Your existence, no matter how short, gives meaning to the universe. Because when you turn your eyes to the sky, you're not just looking at stars, you're ending the universe's 13.8 billion year loneliness. And in that brief moment, you touch both the past and the future. The third paradox is about loneliness and togetherness. On one hand, there is the incredible emptiness that Webb shows us, the millions of light years of distance between galaxies, the vast regions of nothingness like the Buddha's void. This creates a sense of cosmic loneliness. Each galaxy, like an island in the ocean, is hopelessly far from the others, and each star system is another lonely island within its own galaxy. When viewed on this scale, we seem to be alone in this vast, silent, and empty universe. The tragic truth is hidden in the Fermi paradox. If the universe is so big and so old, why haven't we heard a sign from other intelligent life forms? Maybe we are truly alone. Maybe intelligent life is an extremely rare phenomenon that cannot pass a filter the universe cannot overcome. This is the universe's most frightening silence. This is the infinite ringing of an unanswered phone. This is the deep, existential fear of being left alone in the middle of the universe. But, and this is perhaps the most important but, in the face of this cosmic loneliness, stands the incredible truth of togetherness. The complex organic molecules Webb found show that the building blocks of life are universal. The chemistry that makes up you, versus me, a tree, a bird, also exists in a gas cloud 13 billion light years away. Every carbon atom in your body was forged in the heart of a dying star billions of years ago. The iron in your blood was scattered into space by a supernova explosion. This means We all come from the same cosmic origin. We don't just share the same planet, we share the same stardust. No matter how far apart galaxies are, the laws of physics and chemistry that form them are the same. This is a universal language, a universal bond. You are a part of this bond. Every star you see when you look up at the sky is a distant relative of yours. You are a node in this vast network. Maybe we're alone in the universe in terms of intelligence, but chemically, we are never alone. We are the universe itself, and this is perhaps the deepest connection we are looking for. Scale, time, loneliness, and togetherness. These paradoxes presented to us by Webb go beyond scientific data and make us ask the most fundamental questions about what it means to be human. These contrasts are unsettling, but also incredibly hopeful, because they show us that the universe is not just a place to be explored, but also a mirror in which we find ourselves. But this mirror shows us not only who we are, but also what we can be. And there is another paradox Webb shows us, perhaps the most important one, that thin line between destruction and creation. Because the universe seems to use the most violent methods to create the most beautiful things. And in this cycle, perhaps lies a clue to the most fundamental nature of the universe. Therefore, the fourth paradox is the inevitable dance between destruction and creation. On one hand, there is the incredible violence that Webb shows us. Supernova explosions create cosmic shockwaves that tear apart stars and planets. Galaxy collisions rip star systems from their places and fling them into the depths of space. The black holes at the centers of quasars blast their galaxies' gas reserves into space, stopping star formation forever. We see how the pillars of creation are slowly being carved away by the ruthless radiation of the baby stars born within them. The universe is in a constant state of destruction, a chaotic, ruthless, and unforgiving place. The tragic truth is, stability in the universe is an illusion. Everything, at every moment, is in danger of being destroyed by a greater force. The Milky Way will collide with Andromeda in 2 billion years. Our Sun will one day expand and swallow the Earth. The universe itself faces potential ends like the Big Rip or the Big Crunch. This is the sadness brought by the inevitable truth that everything will eventually end. It is the deep weight of knowing that everything created will one day be destroyed. But there is that crucial but. What Webb shows us is that this destruction is never the final word. Every destruction plants the seed of a new creation. When a supernova explodes, it scatters the iron, oxygen, and carbon necessary for life into space, and these elements become the raw material for the next generation of stars and planets. When two galaxies collide, gas clouds are compressed, triggering a new wave of star formation. Even as the pillars of creation are destroyed, the new stars and potential planetary systems being born within them are harbingers of the future. The universe, like a phoenix, is constantly reborn from its own ashes. You are a product of this cycle. Every heavy element in your body was made possible by the violent death of a star billions of years ago. Your existence is a creation that emerged from the aftermath of a destruction. This leaves you with a complex heritage. You are both the child of a star and the orphan of a catastrophe. And throughout your life, you experience this cycle on your own small scale. You build new dreams in place of shattered ones. You start over after relationships end, because the universe has taught you, at the deepest and most fundamental level, that every end is also a new beginning. And this brings us to the fifth and perhaps most unsettling paradox, the blurry line between knowledge and ignorance. On one hand, there is the incredible explosion of the knowledge that Webb provides us. We're collecting data about galaxies, stars, and planets we never knew existed. We are measuring the age, size, chemical composition, and expansion rate of the universe with increasing precision. We have never known so much in human history. Webb is literally a beam of light, piercing the darkness of ignorance. It gives answers to our questions, but the tragic truth is, every answer brings with it dozens of new and more difficult questions. We found the universe-breaker galaxies, but now we must ask, how did they grow so fast? We proved the Hubble tension is not a measurement error, but now we must face the question, why is the law of cosmic expansion changing? We have solidified the existence of dark matter, But now the question, what is this invisible matter, is more burning than ever. What Webb is doing is not expanding the ocean of what we know. Webb is showing us how long the coastline of our ignorance is. We realize that everything we thought we knew is proof of how little we actually know. This is the humbling sorrow of realizing that knowledge is not a final destination, but a constantly expanding horizon. It is knowing that there will always be more, that we will never reach the full answer. But, that indispensable but. This is not a failure. This is science itself. Science is as much about asking the right questions as it is about finding the answers, and Webb gives us the opportunity to ask bigger and deeper questions than ever before in human history. What is more valuable than knowledge itself is the desire to know, curiosity, the passion for discovery, and Webb is the ultimate symbol of this passion. You're in this paradox. Every piece of knowledge you learned in school, read in books, was once the answer to a question someone dared to ask. And you, here today, watching this documentary, are facing the limits of your own ignorance. But, at the same time, you also feel the desire to cross those limits, because being human is partly this, accepting what you don't know, but never giving up on the effort to know. And perhaps the greatest lesson Webb teaches us is this: the universe's greatest mystery is hidden not in the answers, but in the questions themselves. Scale, time, loneliness, creation, and knowledge. These paradoxes form the philosophical map of the new universe Webb has presented to us. This map shows us not only how vast and complex the universe is, but also how strange and special our place in this picture is. We are both insignificant and priceless, both transient and eternal, both alone and connected to everything, both the product of destruction and creation itself, both ignorant and the only beings trying to understand the universe. We now know that the universe was not designed to offer us simple, comforting answers. It is a series of riddles that forces us to think, to question, and to wonder. But as we face these riddles, there is perhaps one more question we should ask. We know that the observable universe has a limit, the cosmic horizon, that final frontier where light has had enough time to reach us. So what about beyond that limit? We know we can never look there, that we will never receive a signal from there. This is a physical reality, but there is nothing to stop our minds from going to that limit. Because the most mysterious, perhaps the most philosophical of the doors Webb has opened for us begins right at that final frontier, and the thought that awaits us at that frontier, is perhaps the deepest and most personal conclusion of this entire journey. So now, let's allow our minds to go to that limit, the cosmic horizon, the end of the observable universe. This is the farthest point, from which light has had enough time to reach us, about 46 billion light-years away. Webb is approaching this limit dangerously, but it can never cross that limit. And beyond that limit, there is almost certainly a much larger universe, perhaps infinite. We will never see it, we will never measure it, we will never know. This is the most absolute limit of knowledge humanity has ever faced. And this limit forces us to confront a series of new and more internal paradoxes. The question is no longer, what is our place in the universe? The question is, what will we do with this knowledge? The first paradox is the tension between certainty and uncertainty. On one hand, there is the incredible precision of measurement Webb offers us. We can measure the distance of a galaxy 13 billion years away, with a margin of error of a few 100 million years. We can detect molecules in an exoplanet's atmosphere from hundreds of light years away. We can calculate the expansion rate of the universe with a 1% margin of error. These numbers are a triumph of human intelligence and engineering. They are concrete evidence, showing that we know some aspects of the universe beyond a shadow of a doubt. But the tragic truth is, as this certainty increases, our uncertainty about the most fundamental issues also increases. We have no idea what dark matter and dark energy, which make up 95% of the universe, are. We don't have the slightest clue why the universe exists, why there is something rather than nothing. Our most precise measurements confront us with our deepest ignorance. The Hubble Tension is the perfect example of this. 67 and 73, two numbers measured with incredible certainty, using two different methods, but they don't agree. This shows that knowledge is like climbing a mountain. As you approach the summit, the view becomes clearer, but at the same time, you also see how many more summits there are and how many are unreachable. But there is that inevitable but. This uncertainty is not a curse, but an invitation. It is the fuel of curiosity. It is the engine of the desire to explore. If we knew everything, there would be nothing left to search for, no questions left to ask. The beauty of the universe lies partly in its mystery. Certainty tells us where we stand, but uncertainty whispers where we can go. You are in this tension. Some things in your life are certain, your name, your past, the basic laws of physics, but your future is uncertain. Your emotions are uncertain. The meaning of your life is uncertain. And you, holding on to these certainties, are trying to find your way in this sea of uncertainties. Because you, like the universe, are both known and unknown, and perhaps living is to dance on that thin line between the two. The second paradox is the strange balance between power and powerlessness. On one hand, there is the Webb telescope itself, a monument to the collective power and intellect of humanity. We designed it, we built it, we placed it at a point 1.5 million kilometers into space without a single mistake. We cooled it to just a few degrees above absolute zero. And now, with it, we are looking at the beginning of time. This is an incredible display of our species' power, a testament to our ability to understand the laws of nature and turn them to our advantage. We may be made of stardust, but now we are looking at that stardust with eyes of our own creation. But the tragic truth is how fragile and limited this power is. We have the power to build Webb, but we do not have the power to protect it from a gamma-ray burst or a major meteor impact. We can solve the universe's smallest secrets, but we struggle to control our own planet's climate, the future of our own species. We build the greatest telescopes, but we cannot overcome our simplest prejudices and disagreements. We act like gods on a cosmic scale, while remaining powerless in our own home. This is our species' greatest and most tragic contradiction. But, that hopeful but again. Being aware of our power and our powerlessness is perhaps the beginning of wisdom. Webb reminds us not only how big the universe is, but also how small and precious we are. It shows us that this small, blue planet is our only refuge in this vast and indifferent universe. Perhaps Webb's greatest lesson is that looking outward is actually a pretext for looking inward. Perhaps our effort to understand the universe is ultimately an effort to understand ourselves. You are part of this paradox. There are things you can control in your life, your career, your relationships, your daily choices. But there are many more things you cannot control. Sickness, loss, the passage of time, and you are trying to strike a balance between this power and powerlessness. While trying to be the master of your own destiny, you're also learning to surrender to the wind of the universe. Because to be human is both to row and to be carried by the current. The third paradox is the thin veil between meaning and meaninglessness. On one hand, the universe, Webb shows us, appears completely meaningless and indifferent, a giant mechanism operating according to the laws of physics. Stars are born, shine, and die. Galaxies collide and merge. Everything proceeds blindly, with neither purpose nor intention. This universe is not aware of your existence. Your joys, your sorrows, your loves mean nothing to it. The tragic truth is, from a cosmic perspective, our lives may be meaningless. In a 13.8 billion year story, an 80-year life is less than a speck of dust. Everything we do, every civilization we build, every poem we write, will be lost like a grain of sand in the ocean of time. This is an existential dread, the deep or dark thought that nothing matters, and this is the most vital, but meaning is not something the universe gives us. Meaning is something we give to the universe. The universe itself may be meaningless, but the moment we look at it and say, how beautiful this is, at that moment, for that moment, we create meaning. Meaning is not an objective reality, but a subjective experience, and this does not make it less real. On the contrary, it makes it more precious because, yeah, it belongs to us. It is our creation. A photograph taken by Webb is just a series of photons and data. But when you look at that photo and feel beauty, wonder, curiosity, and a connection in it, that photo becomes a work of art. You are a meaning-making machine. You are that rare and miraculous being that brings meaning to a meaningless universe. Your life may have no meaning for the universe, but it has meaning for your family, for your friends, for your loved ones, and most importantly, it has meaning for yourself. You are both the author and the hero of your own story, and even if this story is not the universe's greatest story, it is your story, and that is enough to make it important. Certainty and uncertainty, power and powerlessness, meaning and meaninglessness. These final philosophical layers that Webb has opened up for us force us to think not just about the universe, but also about the nature of being human. These paradoxes are unsettling because they don't give us easy answers, but they are also liberating because they give us the responsibility and the opportunity to find our own answers. We now know that our relationship with the universe is not a one-way exploration. It is a mutual dialogue. We observe it, and it, through this observation, reshapes us. But as we approach the end of this dialogue, there is one final concept that brings all these thoughts together, the ultimate destination of this journey. Because everything Webb has shown us seems to point, in the end, to a single truth. And that truth was perhaps in front of our eyes from the very beginning. But to see it, we first had to look 13 billion years away. And now, we understand what that truth is. Because everything Webb has shown us seems to point, in the end, to a single truth. That truth is connection. Therefore, the final philosophical layer of this journey is the illusion of separation and the nature of universal connection. On one hand, there is the idea that everything is separate. You are a separate being from me. We are separate from our planet. Our planet is separate from the solar system. The solar system is separate from the Milky Way. And the Milky Way is a lonely island in this vast ocean of 2 trillion galaxies. This is our daily experience. Separate bodies, separate minds, separate fates. The tragic truth is, this feeling of separation is the fundamental source of pain and fear. Loneliness, loss, alienation. They all stem from feeling separate and disconnected from the rest of the universe. This is the sadness of a leaf, thinking it is separate from the tree it belongs to. This is the fear of a wave, thinking it is separate from the ocean it belongs to. This is the universe's greatest and most convincing illusion. But, and this is the ultimate but our entire journey has led to, every piece of evidence Webb has shown us whispers that this separation is an illusion. At the most fundamental level, we are all made of the same thing. Stardust. There is no difference between the carbon atom in your body and the carbon atom in a nebula 10 billion light-years away. They were forged in the same stellar furnaces, scattered into space by the same supernova explosions. Moreover, we are all subject to the same laws of physics. The gravity that keeps you on the ground is the same gravity that holds galaxies together. The electromagnetism that governs the chemical reactions in your cells is the same electromagnetism that produces the light of the most distant quasars. This means that every part of the universe is connected by invisible threads. You're not something separate from the universe. You are a part of the universe itself that has gained consciousness. You are the universe's way of knowing, understanding, and feeling itself. This is a deep and shattering sense of connection that eradicates the feeling of loneliness. You're at the center of this illusion and this truth. Every day, you wake up as a separate individual. You have your own worries, your own joys. But when you look at the night sky, you can remember that those stars are not just distant points of light. You can remember that they are your origin. And in that moment, in that brief moment, that feeling of separation disappears. And what remains is the deep, peaceful feeling of being one with the universe. You're not a wave, you're the ocean itself. And this brings us to the final paradox, the mysterious relationship between silence and music. On one hand, there is the absolute silence of space, a vacuum. There is no medium for sound to travel. Billions of galaxies, billions of stars, are born, live and die in silence. Supernova explosions, galaxy collisions, the most violent events in the universe, play out like a completely silent movie. Webb brings us the most magnificent images of this silent film, but there is no sound to accompany them. The tragic truth is, the grand symphony of the universe is deaf. Its beauty, its majesty, its drama occurs unheard, unapplauded. This is the cosmic scale version of the philosophical question of a tree falling in the forest, with no one around to hear it. If no one hears it, does the universe have music? This is the deep, melancholic thought that the beauty of the universe is wasted when there is no one to appreciate it. But, one last time, that magic but. Perhaps music is not just sound waves propagating through the air. Perhaps music is pattern, rhythm, harmony. And when viewed from this perspective, the universe is full of music. The orbits of electrons within atoms are a rhythm. The revolution of planets around their stars is a melody. The spiral arms of galaxies are like a frozen harmony. The laws of physics themselves are the notes of the universe's composition. And Webb is an instrument that gives us the ability to read these notes. It translates this silent music into the language of light, colors, spectra, and data. Our job is to interpret this data and give it meaning. Just as a composer looks at notes and hears a symphony in their mind, we can look at Webb's data and hear the music of the universe. This means that music does not exist objectively in the universe, but is created in our minds. We are the listeners who hear the universe's silent composition and turn it into a song. You are part of this orchestra. Your life is a composition with its own rhythm, its own melody, its own ups and downs, and every day you add your own small note to that great symphony of the universe. Perhaps the meaning of life is not just to listen to this music, but also to join it with your own voice. At the end of this long journey, with all these dizzying discoveries, these deep philosophical paradoxes, and these personal reflections, how do you feel? On one hand, there is the feeling of smallness, of insignificance. You feel in the face of this incomprehensible vastness and complexity of the universe, an overwhelming feeling. On the other hand, there is the wonder and pride you feel in the face of the miraculous power of human consciousness that can understand this vast structure, give it meaning, and connect with it. An uplifting feeling. Which one is right? The answer is both. Because to be human is to oscillate between these two, to feel as small as a speck of dust, and yet to have a mind vast enough to embrace the universe, both powerless and powerful, both alone and connected to everything. The greatest lesson Webb has taught us is that these opposites are not a contradiction. They are the two faces of existence, and when we can embrace both, we reach a more holistic and honest understanding of our place in the universe. We now know that the universe is much bigger, much older, much more violent, and much more creative than we thought. We now know that the universe is not just empty, but unimaginably crowded. We now know that there are cracks in our most fundamental models of physics that are unsettling and unexplained. But, at the same time, we now know that we are not just spectators in this cosmic drama, we are part of it. With our bodies made of stardust and our minds that question the universe, we are both the product and the narrator of this story. This long journey started from Webb's lens and progressed to the beginning of time, to the boundaries of the universe, and finally into ourselves. It was a journey from discovery to philosophy, from science to meaning. And now, as this journey comes to an end, we're left with many more questions than answers. But perhaps this is the best outcome, because it shows that the story is not over. It shows that there is still more to discover. And the final image, the final thought that Webb leaves us with, carries a clue, not just about what the universe is, but also about who we can be. Because, after all this knowledge, only one question remains: what now? On this journey, we saw how vast the universe Webb has shown us is, but there's something I didn't tell you. Maybe this isn't the only universe that exists. What if there are an infinite number of universes, each with a different you who made different choices and is living a different life? On our next journey, We will open the door to parallel universes and infinite possibilities. Are you ready?